All right, section 3.7, differentials. So we're going to look at a couple of different things here. One, we're going to talk about locally linear. We're going to be able to look at approximations with tangent lines. And then we're also going to look at differentials. So what can we do? What do we talk about when we talk about locally linear? So if you think about a graph, and if you were to graph any graph, doesn't matter how curvy it is. So maybe we make a very big curvy function. And then we look at just a small little region of that. And if we were to zoom in on this region, that region in there, that looks very close to a line, doesn't it? So again, we could, any region that you want to pick, just in that small region, that local area, we know or we see that that graph is pretty close to a linear function. So that's what we talk about when we talk about locally linear. Locally linear means that any function is pretty close to a line if that region or that interval is very small. So that's the first thing I want to start with here today is comparing values of a function. So if we give you f of x equals 1 plus the sine of x, and we look at the values of the tangent line close to the x values of 0, what do we know about the graph versus that tangent line function? So if I want to find the equation of the tangent line, well, the first thing I got to do then is find my first derivative, don't I? And our first derivative of 1 plus sine of x gives us just the cosine of x. At x equals 0, my equation, I'm going to find my slope, f of 0, I get the cosine of 0, well, not 0, which is 1. So then we can go ahead and write the equation. Oh, actually, we need f of 0 first, don't we, as well? So we have 1 plus the sine of 0. That's where my 0 comes in. So I have 1 plus 0, which is 1. So I get the equation y minus 1 equals our slope, which is 1, times x minus 0, if you wish, or y equals x plus 1. So what does that tell us, and what do we know then about the function? Well, if I want to compare this function with y equals x plus 1, so we can do that in our calculator, or we can do a table. It doesn't really matter to me how we do that. So what I want to do is go ahead and type in this function, which is 1 plus the sine of x. And our second equation is just going to be x plus 1. Again, I want to just look at a small region, a very small region. So if I go to my windows, and I want to look at just a small window. So let's go to negative 1/2, and then to 1/2 for our x values and our y values. Again, negative, well, we can do this. Negative 10 to 10, I guess, will work for now. And if we were to graph that, here comes in our function, and notice what happens. Our other equation isn't there anymore. If I were to zoom out a little bit, say if we went to negative 10 to 10, and I went to graph that, well, here's our function there, isn't it? That's our sine function. And then there is our linear function. Notice what happens in that small region. Notice we can't really discern between what's happening with that. Now we can zoom in, of course. We can zoom in to negative 1 to 1. And there's our function there. And then here comes in our other function. Notice just a little bit of a blurb right there at the end if you saw that. Rewind it if you didn't see that. But just a little blurb. So that function looks very close to what the linear function is. So what does that allow us to do? Well, that allows us to estimate or approximate the value of this function at 0 using the equation of the tangent line. So an approximation of 1 plus sine of x at x equals 0 would be 1. So we could plug that in. Now, again, some of us, actually all of us, should know that the 1 plus the sine of 0 is 0, 1 plus 0 gives you 0. But we're also going to be able to use that equation of the tangent line to be able to show that it's very close. That's going to be very important to us, again, as we solve some other equations and some other problems. So locally linear means to us that a function on a small enough interval is going to be very close to a linear function. And that linear function is the equation of the tangent line. And that equation of the tangent line can be used to approximate the value of a function. And we can go ahead and see that. If you want, I can read it to you, but I'm not going to. You can read. The next thing I want to talk about is differentials and being able to solve a differential. So if I want you to find a differential, all that means is that we're going to solve for dy in terms of dx. So I'm going to get dy on one side, dx on the other. This is going to become very important to us as we get into integration in our chapter 4. So the derivative of y we know is dy dx. Derivative of x to the third gives us 3x squared. To solve or to determine this differential, we're going to take this dx and we're going to move it over with the x's. So we're going to have dy is going to equal 3x squared dx. And that's simply finding the differential or solving the derivative in terms of dy. Here's where it all kind of comes together. So if I want to find a differential to approximate a value, we can approximate a function plus some change in x as being f of x plus that dy. And dy is simply, if we come up here, the derivative of dx, or times the change in x. So what is this useful for? Well, it's useful to be able to approximate square roots or cube roots or anything of that sort. And they like to do this on our exam. Every once in a while, you'll see them ask you to approximate it, and you'll think, oh, I'll just throw it in my calculator. Well, it's either a non-calculator question, or your answer is not going to be exactly what the value of that square root is going to be. So we'll talk about that here in just a little bit. So if I want to approximate the square root of 17, well, I get to determine what my x and my delta x are. If I think about the square root of 17, my function that I'm working with would be the square root of x, isn't it? And if I think about 17, I know I got to find the value of some number. So what number can I plug in for x to get a nice square root that I can work with? Well, if I think about the square root of 17, the square root of 17, again, think about that locally linear idea. 17, a number that's pretty close to 17 would be, yes, 16, wouldn't it? So if I think about my x and my delta x, my x in this case would be 16. My delta x in this case would be 1. So I can go ahead and find then f of 16 plus f prime of x times my delta x. Remember, dx means delta x. In this case, it's going to be 1. So what is f of 16? F of 16, remember my function was the square root of x, so 16 square root of that gives me 4 plus f prime of x. Now I'm going to find the derivative of f. Well, the derivative of the square root of x, off to the side here, square root of x, I can write that as x to the 1/2, so I get 1/2 x to the negative 1/2. If I plug in my 16, f prime of 16 is 1/2 times 16 to the negative 1/2. 16 to the negative 1/2 is 1/4, so I end up with 1/8. So I get 4 plus 1/8. Now if I think about, then times your 1, I guess there, make sure we have that in there. So we have 4 plus just 1/8. 1/8 is 0.125, so I get 4.125. And that's an approximation of 17. If you pull out your calculator, I'm sure you all have it handy there, pretty close. If I take the square root of 17, I get, that is actually equal to 4.123 and some other gibberish numbers. So what are they going to do to us on a multiple choice question? Well, a multiple choice question, they could have A as being 4.123. They could have B as being 4.124, C as being 4.125, and D being 4.126. So if they ask us to approximate this using the idea of locally linear approximations, we know that the answer that we're going to be looking at is C. The actual value would be 4.123, which is a choice, but not a good choice because we're looking for the approximation of this using our locally linear approximations. So you have to be very careful about the wording. If it's a calculator question, they're going to give this to you almost identical to what the actual value is, and it's going to be the wrong answer. So be careful with that. I'm going to go ahead and do a cube root just so we can see how that works. Again, we have to think about this function. I got rid of it there. I'll go ahead and write it down again. F of x plus delta x is approximately f of x plus f prime of x, then our dx, or our delta x, our change in x. So what do we know about the cube root? Well, I know then my function here looks like it's going to be the cube root of x, isn't it? What cube roots do I know that are close to 10? So in this case, I'm going to do 8 plus 2. I know the cube root of 8, don't I? So my approximation for this would be f of 8 plus f prime of my x value, which again is 8, times my delta x. In this case, delta x, the change in x, is going to be 2. So be careful that it's not always going to be 1 like we saw in that last example. Sometimes it could be something else. So in this case, it's 2. So what is f of 8? F of 8 we know is 2. The derivative at 8, well, the derivative at 8, our derivative of our function is 1/3 x to the negative 2/3. So we have 1 over 3 x to 2/3. If I plug in 8, f prime of 8 gives us 1 over 3 times 8 to 2/3. Remember here, from your algebra 2, we can either take it to the second power, so 8 to the second, and then take the cube root of that, or we can take the cube root of it and then square it. I always like to take it down, maybe a smaller number, and then increase it, instead of increasing it and then trying to take the cube root of a very large number. So I get 1 over 3 times 8. The third root of 8 is 2 squared. So we get 1 over 12. So we get 2 and 1/12 as our value. So how close is that to the actual value of the cube root of 8? Oh, I didn't multiply it by 2, did I? So we get 2 and 1/6. My apologies there, 2 and 1/6. So how close is that to our actual value? So if I do the cube root of our 10, forgot what our number was there, it gave us 2.154. If we take 2 and 1/6, that gives us 2.16 repeating. So pretty close, pretty accurate. So that's where our locally linear is going to work, and being able to approximate a square root or a cube root or some value that we know something of. So good luck. If you have questions, give me an email or come see me.